All righty there. All right, we got a clap. All right, that should be good. Yes, yes, Rick. The thing has been hit. Hold on. I should recombobulate myself, get myself in the zone, aka put in the other earpiece so we can have maximal whatever this is that we're doing here. All righty then. So we still have some stuff up on the board. There's a little bit of stuff from this morning here, and we'll let folks start to roll on in because, of course, I am late. Yada yada yada. There's one consistent thing, so I will be late. It's once I am impeccably on time, we should worry about. Okay, so yesterday we ended off on a little bit of, some may say, a cliffhanger. We were talking about the significance of seven, and this for my initial foray into that. We had our friend Jen from the Church Entropy who had joined us yesterday. Uh, she was the first one that started talking about seven. Some may say in a woo-woo fashion, but I would. There seems to be evidence to suggest that it might not just be all woo-woo. Okay, so I erased that part of the board, but what she had originally communicated was the concept that why is it that for us observers like us human beings, us meat bags, why is it typically we can remember typically about seven things, plus or minus two, which might also be interesting there. And again, not all, hashtag not all, but at least for many, we got that type of thing going on here. All right, so we're going to be talking about the significance of seven. And as I used for the little thumbnail there, which I should definitely need to give credit to Wikipedia for at least one of those parts there, we had, we'll start off with this. It has Stoical. Consider that if that was a true circle. All right. Then we put a circle on the inside. And if these were all equidistant, we could do something kind of like this. It's like, yes, I know these are not actually even, but with my error as a meat bag, we're going to entertain this because this is the picture. Anybody that's picked up Thad's book 44, you'll see it in there. And what was the initial interpretation? Well, the initial interpretation, oh God, that's a terrible circle. Hold on, let me make it a little bit more circular there. There we go. I feel a little slightly better. Okay. But we were calling it initially a break in Gale symmetry. Okay. Equals 7. Why? Well, if you have one circle, then you're going to fill it to the maximum of the same size circles. You can put 7. Why? 1, 2, 3, 4, 5, 6, 7. We get an eighth if we include the outside one. But it's almost like we're going up to another level. People may say we're leveling up, so to speak. I need a. Did I wash the shirt? Yeah, I think the shirt is washed. It's just we're wearing this just because, well, it's available and it's wet. I'm wearing it at the current moment. Okay, so that just happens to be a thing with circles. That's very interesting, and that goes on to lay out a bit more elaborate explanation. But let's look at things empirically, if you would. Let's look at the data and see what it might be trying to tell us. Now, okay, as we're, oh my God, I'm not even sure how to spell crock pot. Hold on, let me get to the relevant stuff. Where did I put the little rag? Oh, I tossed it over here because I'm a savage human being. Okay. So we are finding some interesting symmetry between, this is a slight side tangent for those that are really into the deep lore about, you have basically for our energy conversion, our column on the poster there, the tail end seems to always follow something like this. 1 plus or minus, in this case plus, 1/2 of either the imaginary infinite tower power of I or the real part of the infinite tower power of I. So ultimately, as Casey had pointed out, a better way to think of that rather than, oh, they're going to go on for infinity. I raised to the I, so it's all right, rotation, rotation, rotation. All right, but it's the IJK. So we're specifically stating that, all right, we have some form of an orthogonal plane. And now we're going to go, it's orthogonal this way, orthogonal that way, orthogonal this way, and we're going to continue. Okay. We want to be as specific as we can because we're trying to figure out what's actually going on. Okay. Oh, and that's relationship to the square root, aka the 1/2 root of. Oh, this one extends J3 and J4, basically a third and fourth fine structure constants with the first and the second, uh, or as Professor Feynman referred to it, J1 is the amplitude of the fine structure constant. We usually just square it because it's a very useful thing to do. Imagine that. Squaring and square rooting things. Okay. So let's take a look at this. Z sub P. What the heck is that? Well, that's the Planck impedance. What's that? About 29.979 yada 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 ohms. Yes. Not quite that ohm, but it's electrical impedance. All right. You divide it by C, the speed of light, what do we get? Oh, right about 10 to the -7. That's very interesting. Why? Because if we come over here, expressed in meters, kilograms. Oh, okay, that's just what it cancels. Coulomb squared. It's coulombs. Meters, kilograms, coulombs squared. Big C. All right. So if we were to write that out, we have this as our little box symbol that we're just using for notation. This box symbol, just have a box. Basically have an X going through it. Why? Oh, that kind of looks like a cone. Oh, if we were to line this up, oh, those should all be orthogonal to each other. That's kind of cool. We set that equal to, what is it? Is that equal to the Planck mass, M sub P, times the Planck length, L sub P. I divide that whole thing by the Planck charge, Q sub P squared. Okay. What does that get? That gives us approximately, to our calculations, 1 times 10 to the -7. It's technically, was it like 9.999998999 times 10 to the -8, but I mean, who's counting? Uh, it makes a slight difference once you start getting up to around 12 significant digits plus, but typically about under 10 probably doesn't make that much of a difference. Oh, it's kind of like was I think in the Wikipedia article for the atomic mass unit. After the redefinition of SI, we slightly changed some things and everything. It's like for like all practical purposes, for like 10 to the negative till about was it 10 to the -10 is where it starts to go right. They're like for all practical purposes, it's the same. Okay. So as long as you don't need to get that fine to that level of magnitude, you're okay. What happens if we want more? I don't know. But may actually go into a slightly mystery in some of our the things we've been doing that may, let's just say, may ruffle a few feathers, if you would, within maybe the standard community. Again, we could just be wrong. We could just be wrong. Statistics would say that just a couple of random folks out there on the internet, no, you can't notice something fundamental. That's not what happens. You need to be at a very highly funded university with an extremely large uh, donor trust fund and everything to help you. I'm being, I'm ranting a little. I'm ranting a little. It's okay. There's a lot of smart folks in academia that I've learned a lot from. But I digress. Let's get some more folks joining us here. Okay. Oh, we've got snacks and marks. Like to say, the science is ready, everyone. I'm not going to say it's ready. It might be cooking. That could be a potential thing. Because of the oh, yeah. It's well. I I think a lot of folks are feeling that way. I'm not going to say it's a good thing. I'm just going to say I feel a number of other people feel that sentiment. I think the problem with that is a lot of other folks, they might feel that sentiment, and then they're like, well, how do I do something? And they wait until somebody completely rages saying, blah, 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 it's all bunk, blah, blah, oh, shills, 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 yada, yada, insert terms, twist the thing into some political nature and be like, yes, it's all because of them. Who are them? Everyone that doesn't agree with us. Why? Tribalism. All right. I'll try to limit my diatribes, everybody. I apologize. All right. So what the heck has to do with seven? Rick pointed out a very interesting thing. Let's bring that Rick, because it's a very interesting thing because you looked at gravity in an inverse way. I can do this because this is all public and it's already been covered on this channel in Rick's presentation, Archimedes' Law of Gravity. So let's just do this. All right. So you normally got big G. Big G is uh do the magnitude 6.67. I think it's 4. I apologize, Rick, if I'm getting it wrong. It's times 10 to the negative 11 when we express it in the standard metric system here, because that's gravity is, get rid of the circle just because it's taking up a bunch of room. Uh See, this is where looking at things inversely is absolutely fascinating, and that's it's okay. So it's length. All right. So our standard understanding and the way that you would put into Wolfram Alpha to get these numbers, you do the Planck length cubed because it's a volumetric thing. You have the Planck mass in the denominator, and then we've got the Planck time squared in the denominator as well. Why? Because it's an acceleration. Because, okay, if we're going to do the traditional, okay, oh, you get the little fabric of space time, we're doing the curvature. We've all seen that bowling ball in the center, and then you roll another ball, and it's like, it makes so much sense. Okay, first level approximation, number one, you say, this is not exactly what's happening, but this is a totally imperfect analogy to what's kind of going on. And we can kind of make some sense of that because it's like, all right, if you start going downhill, you're on a bicycle. Okay, you start going down. You start off at one point and then, you start going faster. You're going faster. Why? Because of gravity, some form of acceleration. Yada, yada, reference frames, all those caveats and everything. Okay. The interesting thing is if you take the inverse of gravity, you take the big G raised to the -1. Oh my God. I'm going to have to do a video on that. I think the Godzilla fandom will love it. Either that or I'll just aggravate them all because it's like big G -1. I just watched the Godzilla -1 speculation video about the sequel. But if you do this upside down, you get approximately, hold on, let me do this right. Uh, it's it's about a perfect fifth. That's the fancy thing. We can go into our friend Wolfram Alpha here. Uh, yeah, and then we do the other system. It will be 10 to the -8 in that way. Don't I'll try not to bring the science snacks. I'm not a professional chef like some folks. All right, so I'll go over here. We'll bring up our little stuff for the class. All right, all right. So coincident. Oh, we can just do this. Big G -1. There we go. Oh, 1.498 times 10 to the 10 kilograms seconds meters cubed. Oh, that's that's very interesting. So if we do the inverse of that, we get 1.498 times 10 to the 10th. And we're going to flip this upside down. So it's going to be LP cubed, and that's going to be under MPTP. Okay. That's a very interesting thing. And then you can also write that in we won't go into too much detail because this isn't my specialty at all. But you can write as 2 raised to the 7 twelfths in order to get our initial factor there, which is I had never seen this until Rick had pointed this out. So we just do 2 blah 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 7 twelfths. So it seems to be of, I don't know if that's a little bit off than a perfect fifth. It seems to be a wee bit musical in nature, some may say. But oh, hey, K Show, thank you for joining, my friend. All right, we'll get out of that. We just did a little sidetrack thing of very interesting things that some folks can notice if you have the time to think about things, and occasionally a little experience with relevant stuff. So let's get back to 7. So we were talking about our Planck boundary conditions there. Basically, from all the different dimensions of reality, we seem to be able to construct the constants of nature as we know them with 5-dimensional ingredients: time, space, charge, mass, and temperature. Okay, why is it 5? I don't know, it just seems to work out that way. And then within that system, you realize that within the constants of nature themselves, you never have more than 4 of those individual expressions expressed at once. Now you might have like the Planck mass and then divide by the mass of the electron, but it's still the dimension of mass. So that seems to be how, number one, we've gotten the constants of nature initially. Number two, well, we're basically just using that same thing. We're just claiming that we have actual logarithmic closed forms for these things. Oh, I didn't even get to that the other day. That was supposed to be the whole point of the live stream. I think I communicated the basic point. Remind me to save that for the end of this stream so we can actually go through. There are videos. I think there's a playlist on close one of the Planck constants. So we've got them there. Okay. But the interesting thing within those Planck constants, I remember where I left off. So yesterday we were talking about why is it that if we know and have measured, I say measured because it's a two-way speed of light, not necessarily one, we've measured and have the speed of light defined to 9 significant digits. And we have h bar defined at 10 significant digits. Why do we only know the Planck time and length to like 5? We got 7 with the error, but like I think the time one had like 6-0 in the error bars. So the last 2 digits, that's 6th and 7th digit, could swing a decent bit there. So all right, maybe that was for length. I think length was like 1/8 or something. It's a little bit smaller to my recollection. But the interesting thing is, wait a second, the speed of light c, as we colloquially defined it, supposed to be equal to the minimum unit of length, the Planck length, per the minimal unit of time, the Planck time. That's supposed to equal c. It's like, but if we know this to 9 digits, why do we only got these to 5 digits? WTF, mate? Now, again, we do have 7, but it's like, all right, if we just had that, it's like, well, maybe the Planck length is a little greater, so this would adjust this in order to get C. Okay, that's fine. But we got H bar, the elementary unit of action. That's defined as mass area rate. So it's Planck mass, and then it's Planck length squared. So we got a concept of an area, and that's per unit of time. Okay. So we got that. And that's since it's action, if that was squared, that would be energy. But this is action because it's a joule is a measure of energy, and then we express the action by what it does per unit of time. So technically, we're multiplying it by time on top, which cancels the unit on the bottom. That's algebra. Don't worry. Hey, it terrified the hell out of me. If some schmuck like me on the internet can actually start to learn this stuff and actually start to play and actually start to say things that make some sense, think there's a lot of untapped potential out there that people don't know of. That is my opinion there. All right. So the whole point of this is, all right, don't worry about that. But it's all right. If we know this number, the 10 digits. All right. So we get the elementary unit action. We know this the 10 significant digits. It's literally defined. Used to be 12, but there were very large error bars. So they locked it off with the SI redefinition in 2019 that they rolled out through 2021. All right. So 10 significant digits for the elementary unit of action. 9 digits for the maximum speed. Okay. If we get the speed of light to 9 digits, we got H bar to 10 digits. Why do we only have most of these guys to 5? That I think is the question of the day. All right. Now again, I'm not going to say this is the answer. I'm going to posit that this might be a plausible answer. And in order to do this first, we're going to go to a diagram, courtesy of our friends at Wikipedia. Um, so it's the same one I used for the thumbnail. We'll go over here. Boom, boom. We'll go to classical physics. There we go. Yes, it's exactly what it looks like. All right. So this picture is from, looks like Yassine M. Rabet. That's okay. So we're giving some credit there. Thank you, my friend. All right. Let's look at this beautiful bean fudge. What is this? This is the generalizing again. This is just on Wikipedia, and I thought I hadn't seen this until a little while ago, and I'm not sure. I feel like the people that know this, they're like, oh, duh. The people that may not be as familiar, this is basically the core of what we're talking about today. All right. So classical mechanics. What is classical mechanics? All right, we have these arrows, and they're basically talking about relative sizes and relative speeds. Because up here we got meters per second. That's a speed. We've got meters here. All right, we're talking about a size. All right. Classical mechanics is defined as something that is far larger than 10 to the minus 9 meters. So 10 to the negative 9 meters. Something really bitty small, because a meter's about yay big. And then you go down to like a decimeter, a tenth of that. And then you go down to the centimeter. You go down to the millimeter, yada, yada, yada. All right. You got to do that like 9 times. That's ridiculously small. We're getting to the realm of that's probably getting to around like a silver atom or so, maybe a little bit bigger than that. All right. And then classical mechanics is within the realm of far less than 3 times 10 to the 8 meter. Basically, far less than the speed of light. Okay. So basically, classical mechanics speeds way less than the speed of light. Okay. And then far larger than atoms. Okay. What is quantum mechanics? All right. As far as we know, far less than the speed of light for speeds, but near or less than 10 to the minus 9 meters. Okay. Not to the minus 7, but we're starting to get in a magnitude here. And then relativistic mechanics, you're basically talking about at around the speed of light, but for things far larger than the generalized quantum realm. And then you get the QFT quantum field theory, where it's like, all right, we're talking about really tiny things going wicked fast. Okay. All right. If we notice these magnitudes, that's a 9, that's a 9. So what you're saying is if things far larger, but then you're saying within the realm of or less than that. Might it be possible that around these magnitudes somewhere there may be something very interesting going on? And one of the reasons why I say that is also, oh God, who was it? Kurt had him on. It was head of physics department over at Harvard, I think. He was saying that, hold on, I'll bring it up because I never give credit to the right people. It's terrible. And then there was, where are we at? Blah blah blah. It was no, not you, not you. It was ah the oh, where is it? Oh, Jacob. Oh, Jacob Baranidis. So Professor Jacob uh, Barandas. There we go. Hold on, let me share this real quick, just so anybody wants to check it out. Okay, it's there. He has a nice 2+ hour conversation. Apparently, he was presenting this stuff about a year and a half ago uh, on one of the Harvard channels or something like that. He's got a nice talk that he gives. I haven't gone through it yet, but okay. So I can't. Let's say it's a nice talk, but it looks like a nice presentation. Uh, but what he said was really interesting. Uh, I think one could say he's like, unfortunately, I made quantum mechanics boring. And it's like, wait. Um, to quick summary. Okay, I swear we'll get back to it in just give me 1 minute to describe this tangent. All right. So according to the good Harvard professor, the way it was explained was, all right. He's like, I was teaching an intro to physics thing for like first year students and stuff. And I wanted to end the class with just a little bit of a taste of quantum mechanics. And he's like, trying to figure out a good way I could present the material. He's like, every time I try to figure out a way to present the material in an easily digestible way, he's like, I couldn't do it. I would keep on trying to reformulate it. So he's like, ultimately, a couple of years ago, he's like, I wanted to see like if I could kind of find the area where all of a sudden we hop from classical over to quantum. He's like, there seems to be a large chasm behind it. He's like, I wanted to walk along that chasm there and see how close I could get to the point where I say, this is the point where I must jump over. So interestingly enough, he's like, I did that, and I followed it, and I followed it, and that chasm, it seemed to be getting close, seemed to be getting closer. And he's like, to my shock, all of a sudden the chasm went away. And he's like, what's going on here? That's not supposed to happen. Apparently, he made an error. His error was he did not have an axiomatic assumption that he was supposed to have. Um, I'm going to get this wrong, so please, anybody that's interested, go visit Kurt over at the Theories of Everything channel and go see Dr. Barrenby's uh, lectures and presentation over there. Oh, God, I hope I didn't already butcher his name. I apologize, sir. But ultimately, it was a fascinating thing because, to my knowledge, one was supposed to assume Markovian matrices, and basically that's just an underlying dynamic. But within that framework, he like delved into it. He delved into it, and then ultimately, there's a lot of literature on like Markovian matrices and how they work and everything. And then he got to the end of a book, and it's like there's also non-Markovian versions of this, but that is too complex a topic for this talk or this book. And it's like, wait, what? What is going on here? Okay. So ultimately, he worked through it, and apparently there were some folks that had done it before, but they assumed the Markovian dynamics and everything that was going on there. But he said, and again, I could be just butchering this, that when he got down to the small levels, it just appeared to be stochastic. What do I mean by stochastic? You got some billiard balls, you shoot 'em some pool, boom, 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 boom. If you could keep track of all that, I was like, okay, we could probably figure out what's going on. And that's one of the benefits of statistical mechanics is you can use statistics to model the most likely things that you have. And he's sitting here and he's like, okay, this is very interesting. This doesn't seem to, he put it as imagine you're going through a physics textbook or a math book, and you're going through and you're like, oh, I'm learning all this fancy stuff. And all of a sudden you get to the next page, you turn and you're like, it's a blank page. And it's like, well, this doesn't make sense. That's ultimately what his claim was, is there are other ways to help formulate quantum theory. Now, I'm sure I'm the only one out there that may have gotten certain terminology like quantum theory, quantum mechanics, string theory, and just use them all interchangeably like a savage beast. Why? Because I was confused. And the way a lot of folks talk about it, it kind of sounds like they're talking about the same thing. But ultimately, quantum theory was developed because something seems wrong here. Our classical methods seem to kind of be breaking down here. Why? Is it just of a particular magnitude? I don't know. Perhaps. I think it was Professor Brian Greene from the World Science Festival. Uh, and I think and again, I might be misattributing this, but I think he made an offhand comment or something. He was like, yeah, yeah, we got the double slit, our Stern Gerlach experiment and everything. We got our double slit, and then right around 10 to the -7 meters or something, just starts doing its normal thing again. It's like, wait, hold on, time out. Are you saying there's a threshold for stuff to be quote unquote quantum? That's very interesting. That seemed to be like that little picture that we just had up was claiming there. So you don't know, you don't know. Oh, Janet, where's oh, I see Janet there. Welcome. Good to see you, my friend. Yeah, Rick. It's the one where it says there is no wave function question mark yet. Harvard's Jacob Barandez. I think he was listed as like the head of the physics department. So he seems to be a well-established, well-respected scientist, and he's been talking about this for I think he came across it back in like 2022, something like that. So that's something within the past few years. So I'm sitting here, I'm like, wait a second. Are you saying that if we had the ability to actually do even more precision measurements, we might still see a lot of the same things? Maybe there's some wackier stuff going on because if you're really light, maybe inertia is going to feel a little bit different. I don't know. I'm not an elementary particle. I'm some amalgamation of a meat bag that's ranting on the internet right now. But it's it just makes the mind wobble a little bit, or actually get the noggin going. It's like, wait a second, might we have just made a couple of mistakes or something? But then again, it's like, well, number one, like modern creation within chemistry and all these different materials and everything. Pardon my French. That's where science is kicking ass right now. It's people like, oh no, nobody's making advances in physics. A lot of times, what they're talking about the foundations of physics. A lot of folks say, well, it's the foundations. It's like, what do you think you're Einstein? You think you're Bohr or something like that? How dare you do that? And then people will say a lot of mean words to you and everything, and then a lot of folks just kind of get discouraged. They go away and mope and go do something else. Now, maybe that's appropriate. Personally, I think if somebody has spent some time and they got some merit to it, it's something that's worth looking into because yeah, you never know. Because statistically, there's a lot of crazy people out there. You're looking at one right now, but if there's one thing I've learned, it's that crazy people can notice things too. So the interesting thing is, okay, if we have high confidence in our measurements of these different constants of nature, why do we only have these to five? Maybe something interesting is happening at a very particular point. What is the claim particular point? The particular point is right here. That comes out to be approximately 10 to the -7. And what is that? That comes out to be, I believe it's Ampere's constant. Double check. Not amps itself, but it's the constant to generate our amps. Because I think anybody that's ever studied to be an electrician, it's like, no, it ain't the volts that get you. It's the amps. You get 1 amp very quickly. That's not a good thing. That's why Tesla could be like the madman he was and be like, oh, look at this. Oh, 10 million volts of electricity, because it probably wasn't a lot of amps. Again, I'm not a doctor. I'm not saying I've electrocuted myself a couple of times, but that was just different circuits in an old house. Okay, let's just verify what that is and make sure I'm not passing on any fake news here. So let me go back to our friend. You can share with the class. Over here. All right, let's double check. Upper constant. All right. All right. We get into the -7 henries per meter. Blah blah blah. Yeah. Because when you have time, we get time negative there. We get current negative there. So basically, those two units are in the denominator. Time times current is charge. Bada boom. Bada bing. All right. Go to more values. Okay. So basically, we got 10 to the -7 newtons per square ampere. Yes, as our constant there. Now, the very interesting thing, if you take that, let's throw in our good friend C, the speed of light. What do we get? Oh, look, 29.9729245 kilogram meter squared per second cubed ampere squared. What the heck is that? Ohms. Our electrical resistance. Okay, so those of you paying attention, what the heck just happened here? We got something by 10 to the -7. We're taking the speed of light, which we have to 9 digits. Oh, look, we have two actual digits that pop up there, and then we go into our decimal and everything right there. So, what is that also known? Oh, let's go to be able to give us some more units. And what is that come out to? Uh, uh, ba, ba, ba. Oh my God. It's giving us so many. Okay, it's giving us far too many units. There we go. Yes. One Z sub P, one Planck electric impedance. Oh, wait, that's why ZP divided by C is about 10 to the -7. Okay. The other thing that I learned from that is if you go through and you spend enough time staring at all the digits on codata, you're eventually going to start to notice, oh, well, once you get out to about the seventh significant digit, things start getting a little wonky and everything. And it's like, might that be why we're not able to define our Planck units much past five significant digits? Maybe. Now, just a user note. We have a disagreement about charge, but we may have reasons for that being the case. We'll get to that on another day. Oh, hey, Nolan. Da, da, da. It ups volts at the loss. Oh, well, that's interesting. Nolan's saying that Tesla coil ups the volt at the loss of amps. Oh, I'm not sure if that's true, but that makes a lot of sense to me. Or at least sounds right. Uh, well, it seems like maybe there's a conversion right there. Maybe that's an interesting thing to explore. But why is it that some unit involving charge squared, it's almost like we have an orthogonal relationship to charge being squared there, and there seem to be very interesting things that happen. Now, full disclosure, there are other reasons why we have additional confidence. So, for instance, if we go to this is going to be uh, let's go to our poster here. There's there's an updated version where things kind of keep rolling around now. So when we go to our friend over here, get our oh, me. Oh, I should probably actually share it with the class. There we go. Window, boom, there. Okay. So we got our friend here. Okay. The reason why I say we have pretty good confidence is we've got this box basically in the tail end of all these things. Box, 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 box. Yeah, it basically goes all the way down, all the way through. Um, and again, you don't have to agree with exactly what we have. We could be wrong, but there's a lot of things here that the simplicity. Let's just go to a couple of the major ones. Probably the easiest one is, oh, look, H bar. Didn't we just have our friend right there? Yeah, we have that defined at 10 significant digits. And what do we have? We had a mass, we had an area, length squared, divide by time. So it gives us the action. Okay, we have our dimensions there. Those hold for about 7 significant digits, but we have it defined at 10. And what do we need to make that complete? Huh? 1 plus the square root of zeta of 2. Oh, all the mathematicians may have just started to pay attention. But yes, that seems to pop in here. And then we have this is our ja theta. So that's one of the trigonometric forms of our fine structure constants there, squared with our little box, because what that 10 to the negative 7 does, and to be fair, we should define it as either the absolute value of that by basically just taking the number and kind of like canceling out the dimensions. This also may be a very interesting thing because apparently there's something called dimensional mixing. So what the heck is dimensional mixing? Well, at certain energies and intensities, dimensions kind of decohere. They kind of lose some of their meaning and they may become something else. Why is that? I have no idea. You can try looking that up. My best just conjecture with this is like, well, maybe once you exceed a certain threshold or something, um, different actions may occur, different dimensions. Maybe they don't necessarily have a certain meaning uh, to beings of meterish and tens and uh, if you want, you might have to put something into your ear because I re-listened and it cancels out pretty much everything. I know if you want to do something, no, go for it, go for it. I'll narrate. I'll narrate. So, all right, that is stuff to add. So, yeah, you can. I've already taken pictures, so we're good. Right. So we've got a little inversion box, but we're using that as notation for Planck length times Planck mass over Planck charge squared. Yep. Yep. So if we just do the absolute value would be how we come up. Okay, so we're referencing a gap between the double sheet hyperboloid and then we have our single sheeted hyperboloid, which would kind of be the outsides, kind of skimming over. Yeah. Uh, okay. So basically we're setting a magnitude style scale for the conversation that we're having. Yep. Okay, cool. No, I mean that sounds well, that's basically what we're saying right now. Well, I mean that is what that just said. So and it seems to be working because it all kind of like really well, it may literally depend on how you slice it. Because all right, if you slice this way, it's like, all right, we're gonna cone. We go this way. What are you gonna have? You're gonna have a circle. Slice a little this way. Oh, you're gonna have an ellipse. Okay, what if you slice like this way? It's like, well, over here you're gonna have a parabola. What happens if you do this way? Oh, look, and you get some hyperbolas or the yeah, two-sheeted hyperboloid, because this is how it would appear on a graph. It's like, all right, those are very interesting things. Now we just got to map them to reality, and that's ultimately where the rest of the model would come in there. Because right now, the big thing is Thad's working to complete things to get things to work within our poster here in the most coherent way possible. But see what the Transformers mean. Transformers, robots in disguise. I feel like there's plenty of Transformers memes we could use for multiple things in the future. Okay, back over here. Okay. Well, the whole thing is, and the reason why I brought up the good doctor from Harvard is he was talking about stochastic things. Now, if for those of you that might be more professional scientists, or those of you that are just kind of get a kick out of looking at physical things and methods for quantifying or trying to describe reality, um, I don't see any wave function here. I mean, this seems to be a lot more of almost a classical style of physics. All we're really kind of doing is we're just setting our offset. Yes, that. Oh, oh. So wait. So our okay. So the standard way of expressing it is just going to do e the base of natural logarithms to was it pi I to the k and everything for our numbers and our rotations. Oh, that actually goes back to our Planck constants and everything and their closed logarithmic forms, which again, at least according to John Mould, without even seeing them, he's like, oh, well, if one was to try to do something like that, that sounds like it could actually work. So, hey, that's what we're betting on. But because it helps express more information. But ultimately, well, actually, that little, oh, well, let me, okay, so folks can actually see what we're saying. I'll bring this a little closer. The little shiny shadows are, no, that made it worse. Oh, there we go. All right, so this is basically right over here. Basically, if we're going to try to make a wave, we would do e raised to the k pi I. All right. We got our waviness there. But what I'm just simply trying to communicate is maybe we don't always need, maybe there are other ways, uh, or let's just say other models one could use proposing quantum theories in order to go about describing what's going on. And since we have that point built in to what we're doing, maybe there's something there. But don't believe me. Believe Professor Roger Penrose, because we have a little video on that. Because we originally, I think we were misattributing it to Professor Brian Greene, but we go to our friend, the internet, bring right up 7. Okay, 7. God. Uh, okay, too many sevens. 7 significant. Okay. But here we go. All right. So this is a clip from. Unfortunately, Professor Penrose has not reversed aging. He's not that great of a time wizard yet. But this is from him sitting down with Robert Lawrence Kuhn on Newton and Edison's precision on gravity.
Now, mathematics can also describe things in the ordinary physical world, gravitational attraction, electromagnetic attraction, and with the same kind of descriptive accuracy.
Well, there's another, even more in a certain sense. Newton's theory already had a precision of something like 1 part in 10 to the 7. So that's 10 million.
Wow.
And then Einstein comes along and produces a theory which is now known to have a precision something like 10 to the power 14.
So what does that now begin to tell us about what mathematics really is?
Yes, well, in a sense, this is telling us that our picture of physical reality depends on something in the sense which is more precise, at least in our understanding of it, than how we think about the world. It has its own life, in a sense.
Okay. So 2 quick notes there. Professor Penrose had shared that apparently the precision of the Newtonian gravitational constant, big G, for describing gravity has a precision of 10 to the 7. Then Einstein comes along, he formulates GR, and that gives us a precision approximately of 10 to the 14. I don't know about you guys, but apparently 14 is twice of 7. The part of where we're generally thinking, and again could be wrong, is what if the measurements for our constants of nature, we only need 14 significant digits? The other thing you could do is just check on CODAT and see that none of these measurements go past 14 significant digits. That would be the empirical way to go about and formulate a hypothesis there. But it's very interesting because it almost seems like reality might be getting pieced together if you would. Now, does that mean that all of a sudden we know the answer to life, the universe, and everything? No. Might that be coming? Perhaps. But it's just a fascinating thing because it's like you sit there and people, and even when you just being conscious of that, just that 10 to the negative 7, or if you were to invert that, you're going to get about 10 to the 7. I know that goes into Rick's formulation for Archimedes' law of gravity and everything. And it's like, huh, 7 seems to be pretty special. And perhaps a little bit more than just a lucky number. Perhaps it is built in. Oh, another cool thing with 7 is we just do the standard. Don't worry, we're not going to do all the crazy jazz. We're just going to show a little fun thing. And what's this little fun thing? Or we're going to show the power of 7 and perhaps its irrationality. So we go over here. Mad no doubt auto playing in my background. It's okay. We'll close that out. All right. So we take a random number. Let's 15. Okay, maybe divide by 7. Okay, what do we get? All right. This is irreducible. It's going to go on and on, my friends. All right. Don't worry about it. All you need to really pay attention to is I divided 17 by 7. All right. Now, it gives us a repeating decimal. What do I mean? It gives us 4, 2, 8, 5, 7, 1. So basically, it's going to have 6 digits, and that's just going to continue to repeat. Okay. So what happens? Let's do 23 divided by 7. Okay. It's irreducible. What's this? A period of 6 repeating decimals again? 2, 8, 5, 7, 1, 4. Those sound kind of familiar. All right, well, let's go to 9, 8, 7. I don't know. Okay, that gives us the whole number. All right, 9, 8, 8. There we go. That was actually divisible by 7. Okay, what's this? Oh, it's giving us a repeating series of 6 digits again. 1, 4, 2, 8, 5, 7. The interesting thing, if one's noticing a pattern here, we're going to get these same digits in different organizational forms repeating. Yes, the digits 1, 2, 4, 5, 7, and 8 will continually repeat unless let's divide it into something, I don't know, irrational. Let's do E, based on natural logarithms. Oh, it's not giving us a repeating decimal. It's just a confusing number. Oh, okay, maybe just a fluke. Let's try pi. Pi divided by 7. Oh, it's a transcendental number, apparently. Oh, it's not giving us repeats anymore. I mean, that's just a fun thing with 7 over there. And yeah, got what else is that? So again, this seems to be working within base 10. We have our standard combinatorial relations. Oh, hey, Ernesto, good to see you visiting from the old Twitters and everything. And to me, it will always be Twitter, even if I name it something else. I start to refer to it as something else. But let's see, where do we go here? All right, so the moral of the story, we'll bring it up for those who may be joining us. So we go to our friends over at CodeAdder. Let me bring it up to share with the class. All right, we got our little window over here. HBAR. I visit the site very often, if you couldn't tell. Okay, so we got this. We got our 10 significant digits here. So we got like 9. I got 10. Okay, so let's go through other things. Let's do speed of light. Bum, bum, bum. Speed of light in a vacuum. All right, define. 1, 2, 3, 4, 5, 6, 7, 8, 9 digits. Okay, we got all those digits there. All right, let's look up our Planck, friends. Planck time. Okay. So here we got 1, 2, 3, 4, 5, 6, 7 digits. Oh, oh, 60 for error in the last 2. That's pretty large. Okay, let's go back. All right, so I got 5 digits of confidence. Remember, we know the speed of light to 9 and h bar to 10. They both have units of time in it. Go to length. Okay. Again, we have 7 total digits. The last two have error of 18. Okay, that's a lot smaller than 60 in the last two. But we still only have 5 actual digits that we really know. Huh. It was a little frustrating. Well, let's go to the Planck mass. Same thing. We got a total 1, 2, 3, 4, 5, 6, 7. 7 significant digits. But we got 24 in the last two, meaning that, we still only know 5. This is getting a little frustrating, isn't it? I got the blank temperature. All right. Again, 1, 2, 3 digits. 4, 5, 6, 7 digits. 7 digits. And then we got error of 16 in the last two there. Okay. So we got that. And yeah, so we only really know 5 significant digits. Again, Planck charge is a slightly different story. They don't even have it here. It's not even listed on CoData, and that may beggar a number of other questions potentially. But we have this agreement with Wolfram, and seeing as that's basically our primary tool that we're using to help decode a lot of this stuff, it's like to just be open and transparent about that. But we'll wrap up with this. Okay, yeah. Yeah. They need 4 digits. Capricar's constant. Yeah. Oh, after 7 iterations. Oh, that. How do I spell that again? KAP. One more time. Okay, got it. Okay, so I'll just share this fun thing. That was talking about Kepler's constant. So basically, is the number 6174, which apparently, let's go to it. It's constant that arises when we take a 4-digit integer, form the largest and smallest numbers from its digits, and then take the largest and smallest numbers and subtract these two numbers. Continuing with this process, hold on, 6174 is Kepler's constant. Let me see. Okay, here's the actual rule. According to Wikipedia, take any 4-digit number using at least 2 different digits. Leading zeros are allowed. Okay. Arrange the digits in descending and then in ascending order to get 2 4-digit numbers, adding leading zeros if necessary. Subtract the smaller number from the bigger number. Go back to step 2, rinse and repeat. If you continue that within 7 iterations in its most, you're going to reach that 6174 number. And it's going to stay there. So that's okay. So the other thing, we'll just do this. You can see here. Basically, you take those numbers, it's 18 cubed, 18 squared, plus 18 to the first. We sum those digits, we get 18, and then we go down to the 495, we get 18. Okay. 18, which is our claimed number of derangements on the charge boundary, which, coincidentally, what we got there? Oh, we got charge squared. Oh, that's very interesting. Now, again, is any of this, direct evidence saying, oh my God, it's just, I hear a lot of folks, and a lot of folks are coming up with different formulations, and it's like, we have the simpler formulation. We get X constant to 6 significant digits. That's fantastic. That's great. I'm not saying it's wrong. It's just, if, at least from history, good old Professor Isaac Newton developed Newtonian gravitational constant and saw that relationship, and we were able to get it out to a precision of 7 significant digits. And Professor Einstein comes along, does GR and everything. So with general relativity, the framework, you can get to 14 significant digits of accuracy. Now, what if that's all we needed? What if we just ultimately need to just start quantifying the rest of our building blocks of the standard model to recreate the constants of nature? Now, that would take an incredible amount of work a lot of time. You're going to need to have peace. You're going to need to try to like focus on that, and maybe not have the pressure of, so have you published yet this quarter? Have you published yet this quarter? Have you published yet? Because I'm just saying human beings are complicated creatures, and perhaps freedom of thought is a very useful thing. So I'm not sure that's how we're going to get a Volkswagen logo, but then again, they do make some good cars, Nolan. But that's all right. We've been going for about an hour, so tomorrow we'll see where we get to tomorrow. We'll probably actually go over like the closed forms and what we're claiming and the power of logs. Why? Because I'm going to claim logs are useful. So other than that, thank you all for joining. Take care of yourselves, everyone. It's a wacky and wild world out there, but hey, it's open for a better tomorrow. Peace out, everybody.